Okay, nice to meet you, everyone. I'm very happy and honored to be the last presenter to conclude uh, both this session and the exciting first day. Okay, so today I'm very excited to sh- tell you something which we think we know we are very familiar with, but actually we might not. Okay, so it's about BLAST, which we use daily. This is a joint work with uh, Dr. Bill Noble, sitting right there, and Dr. Yuri Cage from University of Sydney. So myself, I'm a junior faculty at the University of Washington. Oh, sorry, University of Waterloo, uh, Department of Computer Science. Okay, let's start. So BLAST, or Basic Alignment, Local Alignment Search Tool, is a fundamental tool of biomedical research. Arguably, it has been the most widely used program in bioinformatics. And in the past 30 years, it has almost around 200,000 accumulated citations. It has been used daily, both in academia and industry, to study the sequence comparison as well as this database search. So according to the New York Times, BLAST is essentially the Google of biological research. There are a lot of applications of BLAST to study the functional and evolution relationships, for example, to trace the COVID-19 evolution, to construct the tree of life, or to predict protein structure. It is a very, very essential pre-processing of AlphaFold. So the workflow of BLAST, uh, especially for protein database search, works as follows. Given a query protein as input, BLAST will search it against a protein database. It will induce a ranking list of proteins in the database based on some alignment scores. So, so that the higher ranked proteins will be more similar to the input query protein. So I mentioned the alignment score. Essentially, the key of alignment score is to do a local alignment between the query protein as well as each database proteins based on some scoring scheme. Okay. So the details of scoring scheme is not very important in this talk, but essentially it comprises of a substitution matrix as well as the gap open and extension penalties. So essentially, it will reward the pairwise matching between two sequences, and meanwhile penalize the pairwise mismatches or insertion deletions. The reason why BLAST is so popular in the past 30 years is because it provides a confidence estimation for each of these alignment in the matrix called e-value, okay, which I will explain later in next slides. And this e-value tells you statistically to what extent you can believe your result. Okay. So in the past 30 years, researchers have drawn numerous conclusions based on e-values and reported countless scientific discoveries, okay, without, without doubting whether this e-value is possibly problematic. So here is how BLAST e-value defined. Okay. This BLAST e-value is defined as the expected number of alignment so that its alignment score is at least as large as a specified number S. Okay. Assuming that both the query and the database sequences are independently and randomly generated. Okay. So based on some theory, that the probability of finding such an alignment uh, follows a Gumbel extreme value distribution, which we might skip some details here. We can derive the formulation of BLAST e-value as follows. Okay. The key idea here is this e-value is dependent on the query protein length. It is dependent on the total database length. And additionally, it depends on two Gumbel distribution parameters. So the first parameter, K, is a location parameter, analogous to the mean in Gaussian distribution. The second parameter, lambda, is a rate parameter, analogous to the reciprocal of variance in Gaussian distribution. So it is important to note that both this K and lambda, they are pre-estimated through extensive simulations for a very limited set of selected scoring schemes. They are pre-calculated and provided as part of the software built-in. Because they are pre-calculated, that means it is totally independent of the database itself, which we will search later. Right? So intuitively, this sounds pragmatic because the protein sequences in the database could be arbitrarily correlated. Definitely, it will affect the estimation of E-value. To verify our intuition, we conducted extensive simulations. Okay. So for example, here, we just choose a random protein. We shuffle it for 1 million times. Okay. And for each of these shuffles, we search it against a very commonly used protein domain database called SCOPE, using this scoring scheme, Blossom 45, with default settings of gap open extension parameter. And because these 1 million shuffles, they don't exist in the database. They are all bad. Okay. Therefore, we expect that the resultant, and so for each of this query, right, we keep the best alignment score. Because they are equally bad, so we expect that this 1 million resultant E-values should be uniformly distributed along this diagonal in terms of the CDF, the cumulative distribution function. However, what we observe is a very notable significance overestimation. What does that mean? That means BLAST erroneously reports a lot of significant identification or discovery, which should be false. Okay. To make it more concrete, we expect only 5% of the alignment should have E-value less than 0.05. However, we observe 11%, more than twice. And we should expect less than 0.1% of alignment with E-value less than 0.0001. But we observe instead 0.46%, more than 4 times as large. You may wonder, this may not be a problem, right? We can simply use a more stringent E-value cutoff threshold. Will that solve the problem? The answer is no. Okay, we did another experiment. We used the same 1 million shuffles of random protein. We searched against another commonly used protein database called SwissProt with another scoring scheme, PAM70, with this default gap extension and open penalties. And now we can see we observe a very notable significance underestimation. Reversely, what does that mean? That means BLAST essentially missed a lot of significant discovery, which should have been included. Okay, we missed a lot of signs. To make it more concrete, we should expect less than 5% of alignment with BLAST E-value less than 0.05. But actually, we only observe 0.8%, less than 20% of the expected number. And we should expect around 100 alignment with E-value less than 0.0001, but we only identify 4. We lose a lot of discovery. Okay. So to sum up, the BLAST E-value can be either overestimating or underestimating. It is arbitrary. So the nightmare is this problem is universal. Okay. So we tested on different implementations, such as the AB BLAST, previously known as the Washington U BLAST, or the FASTA sequence comparison, or different extensions of BLAST, such as SciBLAST, Diamond. I heard someone mention Diamond earlier, right? MMSeq2, and even different settings, such as the nucleotide BLAST. They all suffer the same problem. So now, let's do some troubleshooting. Why? So we start from the very beginning to investigate the most classic theoretical result, whether the probability of finding an alignment follows the Gumbel distribution. What we did is we just fit using the maximum likelihood estimate to fit a Gumbel distribution based on this 1 million 1 million e-values from the shuffled sequences. We fit the Gumbel distribution, and then we calculate the p-value for each of the scores subject to this fitted Gumbel distribution. What we found is, okay, we see this ideal linear trend, meaning that the good news is the fundamental theoretical result, the Gumbel distribution, still hold, even though this is not IID sequence. But the bad news is it is dependent on the database itself. Okay. To summarize, now we are facing a dilemma between statistical accuracy and computational feasibility. The conventional BLAST e-value, it is fast because it uses pre-estimated Gumbel parameter. It only depends on the scoring scheme. However, as we showed earlier, the statistical estimation, the e-value, might be problematic. For the Gumbel fitted p-value, we showed earlier, this is valid. However, it estimates the Gumbel parameter in real time. It depends on the scoring scheme, query, and the database. Okay, so it is statistically valid, but definitely we cannot afford to do 1 million shuffle every time when we search a database. So therefore, we propose studentized Gumbel p-value, or short as SGP value, and it can achieve both statistical accuracy and the computational feasibility. And it's also important to note that by design, it can be very generally applicable to any scoring scheme we want without doing extensive simulations to calculate the Gumbel parameter. Okay. So from high level, this SGP value, we draw the inspiration from the setting that if we want to assign a significant score to an observed values under the Gaussian distribution. Okay. If the Gaussian parameter, right, mean and mu and sigma, if they are known, we can simply standardize the observed values, right, and then test it under this standard normal distribution. But usually, when this mu and variance, right, the Gaussian parameters, they are unknown, we need to do one extra step. Specifically, we need to first estimate the sample mean and the sample variance from some null samples. And then we use this sample mean and the sample variance to studentize the observed values and then test it under the T distribution. It is important to note that for this studentization applies to any family of the distribution characterized by the location and the scale parameter, including Gumbel. So here is the workflow of SGP value. So still given this input, the query protein as input, we will search using BLAST to search this database and report the alignment to the alignment score. So this is as usual. Meanwhile, we will try to shuffle the input query protein a handful of times, say 50. And then for these shuffled proteins, each of them, we will search against the BLAST, using BLAST against the database. And each time, we report the best reported the alignment scores. Okay, so denoted as Ys. Okay, so for the original one, we denote as S. And these Ys will serve as the nulls, okay, to studentize the observed alignment score S. Okay, so essentially what we do is we use this null to studentize, to calculate the sample mean and the sample variance, and to studentize this observed alignment score, and subsequently test it under this studentized Gumbel distribution. Okay. What we end up with is, so for the BLAST, it will report a ranking list of proteins together with these alignment scores. Additionally, we will report this SGP value, which is statistically valid, as I will show later. Okay. Important to know that although it requires where we calculate this sample now, right? It is dependent on the scoring scheme, dependent on database. But when we studentize it, okay, this studentized value, actually, it is totally independent of the scoring scheme and database, making our method very widely applicable. Okay. Now we revisit the simulation studies we showed earlier. So this is the BLAST e-value, which shows notable significance overestimation. And this is the Gumbel p-value involving 1 million shuffles. And for our SGP values, only using 50 perturbations, we can achieve almost identical statistical inference as these Gumbel p-values. So this is applicable in both setting of significance overestimation, as well as this significance underestimation. Okay. So lastly, we will apply our SGP value to a real setting. Okay. So we choose a database called S240. So this is a commonly known protein database, domain database. Okay. So we want to search every sequence in the database against itself. The motivation is we want to find out for each of the sequence its homologous sequences among all protein domains. So, and we can just investigate whether these two proteins, the protein homolog can be evaluated by whether two proteins they share the same superfamily label. And to compare BLAST E value as well as our SGP values, we use a matrix defined as the number of reported homologous sequence, right, subject to some commonly used cutoff threshold, say 1%. So we first use this scoring scheme, the PAM70. We showed earlier that this PAM70 suffers a severe significance underestimation problem. So that's why, as we expected, okay, when we use SGP value, we can report more identifications, almost none. And next, we use a very rarely seen, so it's a different scoring scheme called PFA-sum. This is a substitution matrix specifically designed for protein domain by encoding this protein structure information. And because this is out of the scope of BLAST scoring scheme, so BLAST cannot do that. But we can show that it identifies way more homologous sequences as we expected. Okay. So next step, we will try to extend SGP value to different settings, such as how about we use machine learning to skip these 50 perturbations, like as the extra cost. How about we extend to different settings of BLAST, different extensions of BLAST. This is our next step. And lastly, so let me conclude. So we report the problem of BLAST, the first ever in the past 30 years. Okay. So the key idea is the problem is universal, and we provide a valid solution. And it is independent of the any scoring scheme. And because BLAST is so universally used, so potentially it will reshape a lot of conclusions drawn previously. So one more advertisement. So I will do another part.
Let's stop that advertisement, okay?
Questions.
So we don't have time.